Alrighty, everybody, this is 7-1. We're starting chapter 7, rational expressions and functions. So I'm going to be doing some different work with rational expressions, which are things that come from the word ratio, like a fraction. So we're going to be looking at different algebraic expressions that are written out as fractions. So there's a lot of different things and operations we're going to do with them, but really before we can get into that, we need to talk about, when we deal with a fraction anyway, something about the domain. So what we're going to deal with is look at what kinds of numbers can we use even before we get into doing operations with them. So when we talk about domains, if you remember what domain and range, and we talked about that earlier for functions, domain is looking at those input numbers, the independent variable or the x values. So what we're going to be looking at is what kinds of numbers are okay to use. If we have a fraction, we know that we sometimes have to deal with division, and we can't divide by 0 and get a real number answer. So we really worry about when we look at the fraction that the denominator can't ever be equal to 0. So when we talk about domain, we have to make sure it's all the real numbers except those that make the denominator equal to 0. Those are the ones that we're going to have to worry about. We need to make sure that when we divide, we want a real number answer. So we can't have the denominator equal to 0. So before we start using these rational expressions, fractions, we need to make sure we double check what's okay to use. So to find our domain then, we set our denominator equal to 0. So set that denominator, whatever it is, of your fraction. So set the denominator equal to 0, and then we're going to solve. So we want to see what makes that denominator 0. Anything that makes the denominator 0, we want to leave out of the domain. We want to exclude it. So another way to say that is excluded values. We want to find the numbers that we leave out. So if you think about, hey, I'm excluding you for something, that means I'm leaving you out. So if you're excluded, you're not part of that set. So really what we're trying to do in a domain situation is we're trying to figure out what can we use? Well, sometimes it's easier to figure out what can't you use? So we're going to be looking for those excluded values. So we'll talk about that in these first few. So let's take a look at a function so we can get an example of this. So the first fraction is 2 over x minus 5. That rational expression, ratio, right? It's a ratio of two things. The denominator, whatever values of x might make that 0, are going to be bad because we can't take 2 divided by 0 and get a real number answer. So we have to think about what would make x minus 5 equal to 0 then. That would be something I want to exclude. So set that denominator equal to 0 and solve. Well, that's a pretty easy thing to do, to add 5. So the value of x equals 5 would be a bad deal in this fraction. A lot of people can just look at that and know, like kind of just substitute the number in your head and figure it out. But when the expressions get harder, it's really important to understand that, yeah, we're setting this equal to 0 and we're solving. So x equals 5 has to be excluded. So we'd say x equals 5 is our excluded value, the one we're going to leave out. So if that's the one that we leave out, if x can't be 5, that means I can use everything else except for 5. So when I write that, we can use the set notation. So we're going to be trying to use the braces, the set of all x's. So we talk about x, what it can't be, where x is not equal to 5. It's the only number I can't plug back in. So that's one way to write it. That's called set notation. Some people might say just all real numbers, kind of write it out in words. That's the same thing as saying all real numbers. So all real numbers except x equals 5. Or some people might say all real numbers, like maybe even use the symbol all real numbers x can't be equal to 5. So there's lots of different ways to say it. We could even do interval notation depending on how they want you to write it. Interval notation would be like thinking about what could you use like on a number line. We couldn't have 5. But we could have everything else, so all the numbers less than that and all the numbers greater than that. So just kind of talking about different ways that you may be asked to write it. So that would be all the numbers from negative infinity to 5, and then all numbers from 5 to infinity. So basically, literally everything else except for 5, and that would be union. We're having both of those, either one end or the other. So lots of different ways to say it. Most often, I think for right now, our textbook is going to be writing it this way, just the set notation. But our goal, really our quest here, is to try to figure out, hey, what can't we use? So let's try another one so we can see what that looks like and how we'd write it. So take a look at this ratio. We have x plus 7 over 4x minus 32. We can't divide by 0, so we have to think about what makes that denominator equal to 0. So let's take a peek at that. So if we set that denominator equal to 0, I'm not worried about the numerator. The numerator can be 0 all day long. So 0 divided by a number, like 0 divided by something, like whatever that number is, say it's 8, that's great. That's equal to 0. That's a real number answer. But what we can't do is we can't have the 0 in the denominator. So whatever makes that bottom 0, that's what I'm worried about. So we need to solve that. We need to see what makes that true. So let's subtract 32. So that would give us negative 32, and then divide by 4. So dividing that by 4 would give us a negative 8. If I plugged in a negative 8, I'm going to get 0 in the bottom. I'm not going to get a fraction that has a real number answer. So the domain then, if this is our excluded value, what we can't use, abbreviate a little bit there, if that's the one we exclude, what can we use? Well, everything else. So we can use all real numbers where x can't be equal to negative 8. So when we talk about our set notation, we're talking about what we can use. So we can use basically anything except for that negative 8. So we're looking for what makes those denominators 0. So let's see if we can take it up a level here. Those were linear in the denominator, so degree 1, pretty easy. So let's talk about some other things that can happen. Take a look at the next one. We still have a ratio, right? We have a fraction, and we have a denominator that's a little bit more complicated. So we need to sometimes do a little bit more work to solve that, but the idea is always the same. We're going to take this expression and we're going to set it equal to 0, and we're going to solve. All right, well, this is a degree 2 equation, so it's second degree, right? Look at the highest degree that we have in the exponent, degree 2. Those are quadratics. Those are just like the ones that we've been working with over chapter 6 when we were looking at factoring and doing some of those solutions. So we want to see what factors make this true. What makes the bottom 0? We're just going to see if we can factor that and get those two solutions. So let's remember our factoring. So we're thinking about undoing FOIL. What would you multiply times itself to give you x squared? Well, that would be x times x. Then we have our last term as a negative 18. So we're thinking about things that multiply to negative 18 and add to positive 7. So think of your factors that multiply to 18. Negative, which means, what do we know about the sign? If it's a negative 18, that means one of them has to be positive, one has to be negative. So what multiplies to 18? Well, we've got 1 and 18, 2 and 9, and 3 and 6. So which one of those has a difference of 7? Looks like the 2 and the 9. I think that's the pair we want to go with. And if we want plus 7, which one should be positive? Well, it's going to have to be plus 9 and then the minus 2. So remember our zero product property. When we factor like this, we have two things multiplied together and they equal 0 for your answer. Well, how does that work? Well, the only way you get two things that multiply together and give you 0 for your answer is if one of those things is 0. So we set each of those factors equal to 0 and we solve. So what are our possible excluded values here? Well, just go ahead and solve each of those for x. So subtract 9 and add 2. So we have two things that are excluded, two numbers that won't work. We can use everything in the domain of the function except for these two values. So these are our excluded values, the ones that we're going to leave out of the domain. So literally everything else. So the domain would be all real numbers, so all x's, where x can't be negative 9 or 2. So some people just list like this. Some people might list it x is not equal to negative 9, comma x not equal to 2. If you want to say x for both of those, totally great. We just have to understand that there can be two excluded values or even more. If the denominator were degree 3, gosh, there could be up to 3 excluded values. So we look at that equation we get when we set the bottom equal to 0 and we solve. All right, well, so that means every time we have a fraction, we're going to have an excluded value. So every time you see a fraction, we're going to have to worry about something. Let's take a look at letter D. Look at your denominator. It's 3. If you set that denominator equal to 0, you'd be saying, hey, when is 3 equal to 0? Does that ever happen? Can 3 be 0? No. So are you ever worried about the denominator being 0? No, because it's 3. It's called a constant. That's why they call it a constant. It doesn't change. There's no variable in the denominator. I never have to worry about the denominator being 0. So what can you use for your domain? Well, you have no excluded values. You have nothing that you have to leave out. So if you don't have to leave anything out, what would your domain be? Well, all real numbers. So my domain, when I talk about what this would be everything. I can use all real numbers. So you can use that symbol for all real numbers. Some people use interval notation, negative infinity to infinity. We're showing, oops, parenthesis there. We're showing everything. We don't have to exclude anything because the denominator doesn't have a variable. So don't assume just because there's a fraction that immediately that means there has to be excluded values. Sometimes there might not be. So let's take a look at a couple more and see if we can see what happens in some other situations. So let's take a look at the next one. I have a fraction again, ratio, right? The bottom can't be equal to 0, so let's set it equal to 0. Now this one, there's definitely a variable, so I have to think about it. I have to kind of worry about this a little bit. What would make that 0? So try to think about guessing and checking numbers. A lot of people guess 3, But 3 squared plus 9, that would be 9 plus 9, that'd be 18, so that's not 0. So some people say, oh, -3, -3, let's try that. Okay, we'll plug in -3. -3 squared plus 9. Well, -3 times itself is a positive 9, right? A negative times a negative, so you still get 18. Well, that doesn't get you 0 either. Do I have to exclude anything? Is this factorable? Well, it's not a difference of squares, right? I know both x squared and 9 are perfect squares, but it's not a difference, it's a plus. You're looking for numbers that multiply to 9 and add to 0. There's no middle term. There aren't any. Another way to try to solve this is just subtract 9, just literally solve for the x squared. When you take the square root on both sides, can you take the square root of a negative number and get a real answer? No, there's no real solutions to this. What does that tell you? Well, if there aren't any real numbers that you can plug in to make this 0, there are no excluded values once again. If we tried to graph this parabola, it doesn't cross the x-axis. There literally are no solutions to this. There's no number I have to worry about plugging in again. So no real solutions, that means no excluded values for us once again. So if there aren't any excluded values, what can you use in the domain? Do you have to worry about anything? Absolutely not. So the domain would be all real numbers once again. So just because you see a fraction doesn't mean you're going to have an excluded value. Often you will, but not always. And in this case, we don't because there's nothing that I can plug in there to make it 0. Okay, let's finish up with this one. Just trying to give you some different looks here. So again, we have a fraction. We're worried about the denominator being 0 because remember, you can't divide by 0. What makes that true? So I think we will have an excluded value here. X squared equals 0. What could you put in for x that would make it 0? Well, 0, right? What times itself gives you 0? If you square root, you still get 0 if we undo that. So we do have an excluded value in this one. So I know this one had a squared and we didn't. This one has a squared and we do. It depends what else is with that term. So for this one, yeah, we're going to have something we have to leave out. So x equals 0 is what's excluded. That's what we're going to leave out of the domain. So what can we use? All x's where x is not equal to 0. So we can use every other number except for 0. So we're looking for those excluded values. So our first kind of jump into this rational function idea is to talk about what can we use. We're talking about domain. So we worry about setting that bottom equal to 0. The denominator can't be 0 to get a real number answer. So we solve that equation, set it equal to 0 and solve to figure out what we have to exclude so we know what we can use. So domain of the function. So the assignment for this day 1 for 7-1 is Math Excel. It should be open and it's 13 questions. Put your work on notebook paper so you have your equations. So always set the denominator equal to 0 and solve to find those excluded values.